Hi guys, I'm back for another exercise, also on the pedigree, but this time it's going to be dealing with an autosomal dominant disease, particularly the Huntington's disease. Huntington's disease is a fatal genetic disorder that causes the progressive breakdown of nerve cells in the brain. It's caused by an expansion of a repeating CAG triplet series in the Huntington gene on chromosome number 4. So obviously they are giving us the localization of this gene that causes the Huntington chorea, that it is autosomal, which results in a protein with an abnormally long polyglutamine sequence that causes the degeneration of neurons. There is currently no cure or treatment which can stop, slow, or reverse the progression of the disease. The pedigree represents the inheritance of this disease in a family. As for question number 1, determine if the allele responsible for the disease is dominant or recessive. So as you can notice, this disease is available in every generation, and every affected individual is having an affected parent. So these affected individuals are having their mother affected, this affected male is having his mother affected, and this affected female is having her father affected, which proves that this disease is dominant over the normal allele. So we are going to symbolize the diseased allele, which is dominant, by capital D, and we're going to symbolize the recessive normal one by the small n. As for part 2, discuss the localization of the gene coding for Huntington's disease. First of all, it's given that the localization of the gene is on chromosome number 4, which proves that it is already an autosomal. However, if you are asked another type of action verb which requires logical reasoning, then you're supposed to refer to the pedigree in order to deny that it is neither on the non-homologous segment of Y, nor on the non-homologous segment of X, nor on the homologous segments of X and Y, to prove that it is autosomal. But for this part, for this discuss action verb, the answer that it is located on chromosome number 4 obtained from the given is surely enough. Now we are going to refer to the pedigree to try to figure out the localization of the gene. First of all, if the diseased allele is on the non-homologous segment of Y, clearly if it was on the non-homologous segment of Y, we wouldn't have found the females number 1, 2, 2, 4 and 3, 7 affected, because they do not have any Y chromosome. So this will be an enough clue. For more clues, you can refer to an affected male with his normal, healthy father. So you can say that if the diseased allele is located on the non-homologous part of Y, then the male, in this case is 3, 4, his genotype is supposed to be XY capital D, and he should inherit the Y capital D from his father, but his father appears to be phenotypically normal, so it is not the case. If the diseased allele is on the non-homologous segment of X, in this case we're supposed to refer to the normal female number 3, 5 or 3, 6. So because both of them, 3, 5 and 3, 6, appear to be normal, so their genotypes are supposed to be X small n, X small n. Since if we're talking about 3, 5, since she is normal, her genotype is supposed to be XN, XN, and she's supposed to inherit X small n from her father and X small n from her mother. The mother is normal and she can definitely give the X small n to her daughters. However, the father seems to be phenotypically affected and his genotype is supposed to be X capital D, Y. So in this case, he doesn't have the X small n to give his daughters, and this proves that it is not the case. If it is on the homologous segment of X and Y, usually we have to search for a male and female of the same phenotype, and you have to link their genotypes to the genotype of their father, who's supposed to have a different genotype. However, in this pedigree, this data is not available. This is why we cannot refer to this data from this pedigree. But for other exercises, you have to search for this clue to prove that it is not on the homologous segment of X and Y, which will lead you to know that the localization of the gene in this case is autosomal, since you have already denied that it is neither on the non-homologous segments of X and Y nor on the homologous segment of X and Y, so it is not on a gonosome, which allows us to know that it is located on an autosome. As for part 3, we are asked to write the genotypes of all the family members. So the easiest way to start with is to seek for all the members who are normal in this case, because the normal allele is recessive, and if they are normal, then their genotype is definitely going to be small n. So the genotype of all the normal individuals in this pedigree is of course a small n. These individuals are listed as you can see: 1 1 2 1 2 2 2 3 2 5 2 7 3 1 3 2 3 3 3 5 and 3 6. If we are asked to justify the choice of this genotypes, and then we're supposed to say because they all appear to be phenotypically normal from the pedigree, and we have already proven that the normal allele is the recessive one, so for them to express the normal allele which is recessive, definitely their genotype is supposed to be pure. As for the genotype of 1 2 2 4 2 6, who all appear to be affected, so that their genotype is supposed to be capital D small n, since they are affected, which explains them having the capital D allele, but they have normal children, which allows us to know that these normal children have inherited the small n from their mother and the small n from their father. So since the mother in this case is affected, so she definitely is a carrier, or she's masking the normal allele by the diseased one. So the genotype of these members are capital D small n. The genotype for 3 4 3 7 is also capital D small n, but here we cannot refer to their children, we can only refer to their parents to prove that their genotype is hybrid, because for example, if we're taking into consideration 3 4, you can obviously see that his father is normal, so his genotype is NN, and he will definitely give the N allele to his son, and he will receive the capital D from his mother, and his genotype will be DN. This is also applicable for the member 3 7 in this pedigree. Last question is to determine the risk for the couple 1 1 and 1 2 to give birth to an affected child. If you take a look into this couple 1 1 and 1 2, the genotypes for both of them is already known, and we already know that if the genotype is very well known, you can simply use the table of cross to prove the risk of this couple to have an affected child. So you can simply refer to the table of cross by putting the genotype of the father and that of the mother. In this case, the genotype of the father is small n, and the genotype of the mother is capital D small n. So you simply draw the table of cross, and you will reach out the risk for this couple to have an affected child. As for me, I've chosen our normal rule, which is the risk to have a normal child, which is equals to the probability for the father to be hybrid times probability of this father to give the normal allele, because remember that the diseased allele in this case is dominant, so we're supposed to determine the risk for the couple to have a normal child, okay, times the probability for the mother to be hybrid times the probability to give the normal allele. The father's genotype is small n, so he will surely give the normal allele to his children. So for the probability of the father to be hybrid, we are going to put it 1. He's not hybrid actually, but we cannot put 0 because this is gonna give us a 0 risk, which is not true. So we are going to put it 1. And of course, he is going to give the normal allele. So for the probability to give the normal allele, we are also going to put 1. Now, for the mother to be hybrid, she is necessarily, surely hybrid because she already has a normal children. So her genotype is definitely capital D small n. And because she is hybrid, there is a probability of 1 over 2 to give the normal allele to her children. So in this case, the risk for this couple to have a normal child is 1 times 1 for the father and for him to give the normal allele, times 1 for the mother to be hybrid, times 1 over 2 for this mother to give the normal allele. This is going to give us a risk for this couple to have a normal child 1 over 2, which means that the probability of this couple to have an affected child is 1 minus the answer that we obtained, or 1 minus half, which is equal to half. You are going to reach the same result when you apply the table of cross, since the genotypes are very well known. You are also going to have, because you are going to multiply the small n from the father with capital D and the small n from the mother, which will lead you to know that the risk for this couple to have an affected child is 1 over 2 as well. Thank you all for watching, and I'm going to come back with another videos on other pedigree exercises. Bye.